insulators. Materials, the electrical property of materials. We can divide materials into two groups, conductors and insulators. Well, you know from our earlier discussion that protons are fixed to their relative positions, but electrons are free to move about. Now, but not all electrons are just free. They are confined to their atoms, but motion is associated with electrons. Electrons can move about. Is that right? Electrons are free to move. In some materials, especially metals, electrons that are relatively farther away from the nucleus. You know that electrons actually exist in a cloud around the nucleus. Now, electrons that are comparatively farther away from the nucleus are not very closely attached to the nucleus. That means they tend to move from one atom to the other. In other words, in a metal, there is a cloud of electrons that can move about. You see? Now, that means a metal allows the free flow of electrons in it. And such a material is called a good conductor of electric charges. So, some materials, especially metals, electrons that are relatively at large distances from the core of the atom are rather loosely bound to the atom and are virtually free to move about in the material. Now, let me see if I can show that to you. Give me a second. Here I have an animation that shows how the electrons in the outer orbits, or electrons that are relatively far from the center of each atom, behave. They are virtually free, and you can see they move about. Electrons can move from one atom to the other. You see, those electrons really do not belong to any particular atom. They can be called drifters. That means there are a large number of these kind of drifters in a conductor. All metals are good conductors. Now, that means these electrons can be made to move from one end of the conductor to the other. And that is how we get an electric current. Now, you remember we talked about current. When electric charges are made to move, we have a current. So, a good conductor will allow the motion of electric charges in it. This aluminum rod that I'm holding is a good conductor. That means if I place some excess charge on this, it will spread right through the material. The aluminum allows the free flow of electric charges in it. It is a good conductor of electricity. So such materials are called conductors. Most metals are considered to be good conductors of electric charges. In some other materials, electrons are localized and are not allowed to move from one part of the material to another. Now, this is a good example of such a material. Well, one of those AAAs, a pen, is that right? Plastic. Now, atoms in here, the electrons in the atoms here are localized. They are not allowed to move about. Now, such a material is an insulator. So, materials can be conductors or insulators. Such materials do not allow electric charges to flow through them and are called insulators. Now, both conductors and insulators play vital roles in building of electrical circuits. You see, we are able to enjoy electrical circuits. Our life is so much controlled these days by electrical circuits. When you use a cell phone, you are using a very sophisticated electrical circuit. Now, how is it possible that we are able to use that electrical circuit? because there are conductors and insulators. If all the materials were good conductors of electricity, what would have happened? You would never be able to build an electrical circuit. You will never be able to wire your home to use electricity, because if every object is a good conductor of electricity, all electricity will flow to the earth. We will never be able to use electricity. In fact, our life would be miserable. Well, in fact, there will be no life actually, in fact. So, we owe again a lot of the good things that we enjoy in our life to conductors and insulators. What about interaction between electric charges? Now, how do electric charges interact? What are the two fundamental types of electric charges? Negative charges and positive charges. The fundamental properties of electric charges are: like charges repel. That means two positive charges placed together will move away from each other. Similarly, two negative charges will move away from each other. So, like charges will repel, and unlike charges will attract. A negative charge will attract a positive charge. Unlike charges will attract. Now, a negative charge will attract a positive charge. A negative charge will repel a negative charge. A positive charge will repel a positive charge. The presence of free electric charges can be detected by using an electroscope. This is called an electroscope. Now look at some of the parts of the electroscope. The electroscope has a conducting platform, and it has a conducting stem, and it has a conducting leaf. The leaf is very thin, it can move very easily. So what happens when you place some excess charge on the platform? Because the stem is conducting, it will move along the stem, and that means the leaves are also conducting. So the stem and the leaves will acquire the same type of charge. What will happen? The leaves would then want to move away because the like charges will repel. So the leaves will diverge, and the extent of divergence will give you an idea of the amount of charge placed on the electroscope. An electroscope like the one shown on the left can be used to detect the presence of an electric charge. It consists of a conducting platform, a conducting stem, and a conducting leaf. The stem and the leaves are enclosed in a glass case so that the leaves will not be disturbed. Now, if some excess charge is placed on the platform, it spreads onto the stem and the leaves, which are all conducting. That means as the leaves and the stem acquire similar charges, the leaves move away from the stem. Now, here is an animation of it. Now, you place some excess charge on here. There you are. Now, the stem and the leaves both have the same excess charge. Therefore, the leaves move away. Now, you see what happened when somebody came and touched there. When somebody came and touched, all these excess charges simply disappeared. This is called grounding. We will talk about that. But at the moment you see how the leaves diverge. And the extent of divergence is a measure of the amount of charge. Look at once again. When an amount of charge is placed there, the leaves will diverge. Alright. On the other hand, I want you to look at this one. When an amount of positive charge is placed, again the leaves diverge. Now what happens when you touch it? Now, did the positive charges move away? No, look, when negative charges are moving in to neutralize the positive charges. You see, motion is associated only with negative charges. Positive charges cannot move away. If you touch a positively charged object, negative charges from the earth will come in and neutralize the positively charged object. So the extent of divergence is proportional to the amount of excess charge on the platform. Now, how do you charge? In the beginning of this lesson, I told you that all objects, including my pen, are electrically neutral. Now, I'm going to rub this with my jacket. You know, I'm wearing a jacket made of wool. If I rub this with my jacket, and if you see, there is a small piece of paper lying on this. Now, do you see what happened? That paper jumped onto this pen. Now, what happens? What is the process? Well, the neutral object, which is this pen, is now electrically charged. What happens? When I rubbed it with wool, some electrons from the wool actually got transferred into this pen. That means the pen now has an excess amount of negative charge. It is this excess amount of negative charge that attracted the paper. Now, some time ago, I explained to you that an electroscope can be used to detect the presence of electric charges. Now, I have a very crude model of an electroscope here. Let me try and focus it a bit more. In place of the platform that I showed you in the picture, this is a spherical platform. And this is the conducting stem, and those are the conducting leaves. If I place an excess amount of charge on the sphere, it will spread onto the conducting stem and onto the leaves. Now, let me see if I can do that one more time by rubbing this pen with my wool jacket. And if I am successful, I will be able to place some excess charge onto the electroscope. Did you see what happened? The electroscope is now electrically charged. You see, I placed the electrically charged pen on the platform of the electroscope, which then charged the electroscope. See what happens when I touch it? Well, the charges had actually disappeared. Now, I will be working with this a little more as we go on. So, that obviously means that a neutral object can be electrically charged.